I'm pleased to welcome everybody to our fourth webinar on carbon capture, avoidance and storage and reuse. So CO2 is no longer just a byproduct, but it has become a technical feature which can be used in various industries. And as world leaders have been meeting over the past 2 weeks to try how to abate and avoid and capture CO2, we have now 3 expert speakers who will guide us through the possibilities of using CO2 and how to capture, store it, and use it in various industries. Our first speaker is Andrew Baxter, who joins us from Utah in the US. Andrew co-founded Sustainable Energy Solutions at the end of 2008, and he helped to develop an integrated carbon capture and energy storage technology, which he led through various testing, development, and demonstration phases. Later, his company was acquired by Chart Industries in December 2020. He holds a degree in economics and business and an MBA from Rice University. I'm also joined by Klaus Peyerhuber from Jenbach in Austria. Klaus holds a PhD in mechanical engineering, has been in the industry for 23 years. He's been working with Jenbacher, GE, and now with Inyo Group, and he's currently looking into how to make gas engines ready for hydrogen co-firing in various applications. I'm also joined by Ulrich Schmitz from Atlas Copco Energas in Cologne, Germany. He holds a degree in mechanical engineering from Cologne University. He's been around for 20 years in the industry. He's been working out of Singapore and China and is now back in Cologne. So let's get started and let's get right into the questions. Andrew, can you kick us off by telling us how CCS and carbon reuse helps to decarbonize not only the power sector, but also related industries, especially energy-intensive industries?
Sure. Yeah. Thank you, Anja, and it's great to be here with you and with your audience here. We often talk about this time as an energy transition, and the reason we call it an energy transition is because we're moving from a period when industry and energy has been heavily dependent on fossil fuels without abatement of CO2 emissions to a future where we need to have lower CO2 emissions, but still provide for the quality of life and economic growth that's needed throughout the world. And carbon capture and sequestration and use is really the only way to leverage the assets and the infrastructure that we've put in place over the last decades and simultaneously reduce our CO2 footprint while providing the energy needed around the world for developing countries and for the developed world. And so from a power generation perspective, carbon capture, sequestration, and use is how we can reduce CO2 emissions coming from natural gas plants, from coal plants, from other fossil emitters, and in other industrial sectors like cement and steel and chemicals. Similarly, there's a lot of areas where you just cannot replace a cement plant with a solar panel, right? And so we need to do carbon capture in those cases if we're going to reduce the CO2 emissions coming from those industrial plants and sectors.
Sure. So reducing is one thing, but we are trying to achieve a carbon negative solution, a carbon neutral, but possibly also a carbon negative solution. Klaus, is there a way towards achieving that?
Yeah, thank you, Anja. Of course, there is a lot of talking about direct air carbon capture and then storage of the CO2. I think this is in the early stage, but I think this has a huge potential and will grow significantly over the next years. But on the other side, there is also the biomass, because we are partnering with a company here in Tyrol in Austria that is called Synkraft. They are producing a biomass gasifier, producing syngas, which is then used in a gas engine. And as a byproduct, they are producing black carbon. And this black carbon is used then as a fertilizer. And when we make the balance around the carbon balance around this solution, it comes out a carbon negative.
Wow.
So this is also a solution that is helping to get carbon negative. Another solution with bigger biomass boilers, bigger biomass power plants, and combined with carbon capture storage would also be a carbon negative solution. I think this is something that will come also more in the next couple of years.
Very interesting. Ulrich, where do you see, where is CCS and CCS retrofits most in demand? Maybe in cement or steel or refining? Where does your company has the most exposure?
Yes, hello everyone, and greetings from Cologne, and thanks for listening in. Yeah, of course. Over the years, what has been achieved? Okay, so the carbon capture technology, either amine based or membrane based, typically requires afterwards compression to boost the typically wet CO2 gas to transportation, to pipelines, or to sequestration. So we have seen their activities in the past years, but probably not enough. When you look at the reports, what the IEA issued in the Net Zero 2050, so we are coming from 35 gigatons of CO2 emissions in 2020. And if the world wants to meet the climate goal of Paris, okay, so then it needs to go down to around 4.5. And that means by 2035, 4 gigatons need to be captured. And I think I was just saying, so far it's only around 40. So it's a significant growth has to happen in this regards if the world wants to achieve those targets. And yeah, your question was regarding which industries. Yeah, of course, all the industries are using fossil fuels, and they all have CO2 emissions, and some are easier and some are more difficult. The most of it is probably captured from the natural gas, while there's activity also now around cement. Having that said, there's a cement capturing project ongoing in Norway, the Northern Lights, where the CO2 is then going to be captured from the cement production. Of course, there's other projects as well around the world. While because I'm sitting in Europe, I refer also to Porthos, which is a carbon capture project in the Netherlands, and this helps to decarbonize the port of Rotterdam. And also recently we have been awarded a compressor order to feed into this pipeline. So yes, as I said, there's still a lot to do in this regards. Something has been achieved, but investments and incentives need to follow soon.
Yeah, very interesting. Let's look also into the economics. So we have a lot of technology out there. We can reduce, abate, get to carbon neutral, get to carbon negatives, possibly in some cases. But how can we actually reduce carbon and stay economically viable and cost competitive? Klaus, can you get us started on this?
Yeah, that's a good point. We're talking about carbon capture storage, and you mentioned now, how can we be competitive? Yeah, because carbon capture storage very often comes in combined with hydrogen. And when we talk about hydrogen today, there is a lot of focus on green hydrogen. But more and more hydrogen that comes into play is low carbon hydrogen. And low carbon hydrogen produced out of natural gas combined with carbon capture storage. Both are either low carbon or carbon free. Yeah. The big difference between these two hydrogens is the cost, because low carbon hydrogen, also called blue hydrogen, can be produced fairly competitive. I call it as an upgraded natural gas. because it's a gas that is free of carbon. It has a cost adder in the range of maybe 30 to 50%. And that could be the bridge for the industry to be still cost competitive now, before green hydrogen is becoming more available and more cost competitive.
How do the costs compare? How expensive is blue versus green hydrogen?
How would we compare the cost between? Today, I think the difference between low carbon hydrogen, blue hydrogen, and green hydrogen is still in the range of a factor of 5 and more.
Okay, and I see your point. Andrew, do you want to add to this? Is this also being discussed in the US?
Yeah, certainly, and I agree with Klaus's opinion there, or his analysis, that blue hydrogen or low carbon hydrogen generated from natural gas sources with carbon capture is that's going to be the early the early adopter area for at large scale, at least, for low carbon hydrogen. And we definitely are looking at blue hydrogen projects where we can capture CO2 from hydrogen generation to reduce the carbon footprint of that hydrogen. So that's a really important area as more green hydrogen projects can scale up and become more cost competitive. So I agree with Klaus's there.
Excuse me, at what time are we looking? How long do we need this bridge? And how quickly can we go to, I don't want to say full green hydrogen, but how long do we need blue hydrogen for?
Well, predicting the future is difficult, right? I would say I don't think there's a reason to limit how long we produce blue hydrogen. I think blue hydrogen can be a solution indefinitely. So the limit is more on how quickly green hydrogen can both scale and become cost competitive, and that's tied pretty closely with how quickly renewable energy can scale and be deployed in a broad way. And there's a bit of a competitive feature to that market where you have to decide if you're going to generate renewable electricity. Are you going to use that to generate hydrogen, or are you going to consume that renewable electricity directly? And so there's a lot of different market forces, and it's a little complex to I think, project.
The actual technology would work for blue and for green hydrogen. So this is not the issue, is it?
Sorry,
I understand your turbines, they run on natural gas, on blue or green hydrogen. It's just the cost of the feedstock, basically. Yeah. All right.
Okay.
Ulrich, do you want to jump in, please?
Yeah. Thank you, Anja. Yeah, since you spoke about staying cost competitive, and of course, if you see, so the carbon tax or the carbon price increased also here in Europe now, significant, and of course that is maybe a driver also for this activity as well. But another way would be also to reduce CO2 emissions and greenhouse gas emissions by making use of existing low pressure steam. For example, we have an example what we have done a project in the Netherlands as well, using a low pressure steam from, in this case, from a polyethylene plant. The steam is used for cooling, and then water is used for cooling, and then it returns as a steam on a low pressure. And this steam is then compressed to a higher pressure and is used. And this high pressure steam is used, as a heat source, as process heat. So, and what is now in the interesting part, of course, you can replace the boiler, basically the boiler which is using natural gas, burning natural gas, and emitting CO2. So while doing this with a compressor, okay, you have some electricity cost to absorb, but then you save on the CO2 taxes and you save natural gas. And so that is also a case which supports, let's say, the operation and can be a nice business case for the user as such. Yeah.
Interesting. We actually have 2 questions from the audience. I address this to everybody. A gentleman is asking, what is the best commercially available CO2 technology in the market to date? And what about its economics if it's solvent based? He's talking about post-combustion CO2 recovery. Who wants to take this?
Sounds like a natural fit for me, but I'm happy for anybody else to comment as well. But so I think available today is a key term there. So and the cost and the maturity of the technology are going to depend on the application that you're looking at as well. So the most mature technologies are solvent based, as it sounds like the person who asked the question indicated. So typically amine based technologies, and that's because they've been used and developed for a long time in gas treating. And so those technologies are pretty well known, but more recently have been applied to post-combustion applications. The economics of that are going to depend pretty heavily on the specific application, especially the scale. So you will be able to achieve lower costs with larger deployments of the carbon capture technology. Because of the economies of scale of the capital costs. And then the higher the CO2 concentration, typically in the gas, the lower your energy cost per ton of CO2. Our technology is different than those amine technologies. Our technology is kind of a second generation technology. And it benefits though from the same thing. So larger scale and higher CO2 concentration in a post-combustion source generally will result in better economics for our process. And when you compare us in, say, a natural gas boiler application or a coal-fired power plant application, we typically think we can achieve about half the cost and about half the energy requirement of current kind of first generation amine technologies with our cryogenic carbon capture technology.
Klaus Ulrich, do you want to add to this? Do you have relevant technologies in this field?
No, we are, let's say, we are more downstream on the carbon capture system with our compressors. We take the CO2 gas, which comes basically after the amine system, and then we boost it to different pressure levels depending on what is the use. Yeah. But no, this is not what Atlas Copco is involved in directly. Yeah.
We have a very good question from somebody who seems to be based in Europe. So he's basically saying, are there any successful CCS projects operating at scale? He believes the stuff which has been happening in Europe is pretty weak and small so far. And he says some steel makers say in order for them to get started on green hydrogen as an ion reducing agent, the cost needs to go down to $1 per kilo from currently $7 per kilo. So question, do you agree with these costs? And do you agree with his cost estimate? Do you agree with his view on this? And when do you think this low cost of $1 per kilo for green hydrogen could actually be achieved? Klaus, this is your question.
$1 per kilogram of green hydrogen, that's a fairly low price. Yeah.
He said currently it's 7, but it needs to go down to 1 to be cost competitive. And by when can this be achieved?
Yeah. $1 per kilogram is equivalent to $30 per megawatt hour. And $30 per megawatt hour is or was an average gas price in the last 5-10 years for distributed consumers. It was lower than that the last couple of years. Now it is twice as high. It is at $60 per megawatt hour. So that is the range of natural gas price. I think green hydrogen could be a little bit more expensive in the future, in the range of $1.50 to $2, so that it is suitable to replace fossil fuel in industries and some other applications in transport sector, etc. I'm not sure if it really needs to go down to $1 per kilogram. I think $2 or a little bit below $1.50 would be enough.
And we could achieve that within the next, say, 5 to 10 years at scale by importing hydrogen from Australia, Africa, South America.
That's difficult to say, but I think a 10-year horizon is maybe possible to have that, yeah.
Good, excellent. All right, so this was from our listeners, and now we go back to the questions we have already. I'm starting with Andrew because I understand he has a memorandum, or his company has signed a memorandum with FL Smith on the commercial use of CCS in a US cement plant. So tell us a bit about the economics, about how quickly you implemented this project. The floor is yours.
Yeah, thanks. So, and this might get to the first part of your other question a little bit as well. I think the audience member also asked about how many carbon capture projects have been deployed at scale, and commented that they thought that what had been deployed was pretty weak. And I don't disagree with that comment. So, you know, carbon capture is very much an industry that is nascent. It's an emerging market, emerging industry, emerging technologies, really. And our technology is, as I mentioned, kind of a second generation technology that we've developed over the last 10 years to really prove out the technology and functionality. And we're now working on scaling that technology up. So cement has been a focus area for us because it's a fairly large emitter. Between 7 and 8% of total CO2 emissions around the world come from the cement space, but it also represents a space that cannot easily mitigate their emissions through any other method besides carbon capture. So as you said, we've recently signed a memorandum of understanding with FL Smith, a Copenhagen-based cement-focused engineering company, really a very prominent one in the cement space. In addition to that memorandum of understanding to commercialize our technology within the cement space, we've done several projects and have several that we're working on in that space. So one of the previous ones was one we did as part of the Carbon X Prize, where we captured CO2 from a cement plant in Alabama at a small scale, about 1 ton per day of CO2 capture, and provided that CO2 to Carbon Cure, which is a Canadian company that uses CO2 to cure concrete. And that was the first time in the world that a full life cycle demonstration of capture and use of CO2 within the cement space had been achieved. We just recently announced a project where we will be deploying our technology at a cement plant in Missouri in the United States at 30 tons per day. So we're scaling up from 1 ton to 30 tons per day here in the near term, and that's a project with Eagle Materials. FL Smith is involved in that one as well, and the US Department of Energy.
Very good. There's a question from the audience. They are saying, what is your perception about the social sentiment of storing CO2? It could be potentially seen as damaging, maybe it could escape at some point. Environmentalists don't really like it. Or is there some danger? And are there any physical constraints implied by or in storing CO2 underground? There's aquifers, there's rocks, there's various options. Andrew, do you want to take this one, or who wants to take it?
I could comment on it if you'd like. Yeah, you can kind of divide carbon capture and storage into those two pieces, capture and storage. Our technology focuses on the capture portion, but I think your audience member is wise to ask about the storage piece as well, because we will need both in order to make this industry work and for the market to mature. From my perspective, I'm not a geological expert or a sequestration expert, but I've sat next to many of them and talked to them. And the biggest challenge on the sequestration side, I think, is going to be political and public perception. Geology underground is something we know very well in the energy industry. We've spent a lot of time looking at rocks underground and how things behave in them. But there will need to be some efforts put into, where CO2 can be stored, how it's permitted, who's liable for the CO2 once it's underground, because there's going to be a lot of people who are reluctant to have some CO2 storage in their backyard, right? There's going to be a lot of not in my backyard sentiment.
Yes, somebody, Klaus and Ulrich, maybe you can comment on that as well, but somebody's asking a pretty specific question saying, most CO2 capture technologies available in the market to date seem to work only for flue gases with concentrations above 10%. So do you know any technologies which might be efficient or cost competitive for lower CO2 flue gas concentrations between 2 and 4%, he's asking. Do we know anything?
This is, yeah, go ahead, Klaus.
I'm not an expert on this, but from typical combustion or combustion engines, for example, the concentration is in the range of 8 to 10%. Right. So that's how these carbon capture technologies have been developed around, but I'm not an expert on this technology.
Yeah. So at SES and carbon capture in general, but at SES and Chart, we love seeing Klaus's rich burn engines, because you know, a lean burn engine will have about half the CO2 concentration in the flue gas compared to a rich burn engine, because there's more excess air going through the engine. And what that means essentially is, to capture the same amount of CO2, we have to capture twice, or have to process twice as much gas, right? And so I don't think there's a problem with carbon capture technologies that can capture from low CO2 concentrations. Direct air capture is capturing from very low CO2 concentrations. It's really the economics of, you know, having to process much more gas to capture the same amount of CO2. It means that your cost per ton of CO2 increases significantly as your CO2 concentration decreases. And so, in the sense that this market is an emerging market, and you know, we're kind of looking for the lowest cost options first to capture CO2 from.
Sure. So the same gentleman is addressing you again, Andrew, about what is the largest dry CO2 capture facility you have built so far, say at 6 to 7% CO2 in the flue gas. And can you speak a little bit more on the dry cost of 50% versus amine technology? So can you get us an example of a large project on this technology?
Sure, and by the way, I'm happy for people to reach out to me individually after for, you know, specific questions. We're very open to look at, you know, the energy and economics of specific projects you have, because I'm talking too much, but we'll say that yeah, so the largest project we've done to date is a 1 ton per day demonstration unit that's been demonstrated all the way from about 4% CO2 up to over 25% CO2 on different sources, including natural gas-based sources. And as far as the 50% difference in our cost, typically we are looking for higher CO2 concentration sources to capture from right now. And that's because our cost advantage as a percentage is better there. So when you're at 4 or 5% CO2 at a small scale, which is I'm assuming what people are asking about here in your audience, then you're going to have trouble hitting cost numbers for CO2 capture that would be covered by existing regulations and incentives. Is basically kind of what that comes down to. But again, that's not always the case, and there's other uses for CO2. So sometimes you can find a market where your CO2 might be able to demand a higher price. We can produce CO2 at very high purities as a liquid, and so it can go into things like food processing. And so sometimes you can find you know, markets where that makes sense to capture CO2 at a higher cost, because you can demand a higher price for the CO2.
Yeah, understood. Ulrich, there's a question addressed to you as well. From the audience, some Spanish speaker. Could you please elaborate on how compressing low pressure steam to high pressure steam works technically, and in what application, and how it can be used in the context of this webinar?
Yeah, thank you for the for the question. Great one. Yeah. Yeah, it's doable with a turbo compressor. So the steam is basically coming in as a gas, right? So it is not, of course, not liquid. Is a gas, and it's compressed in the compressor to the level needed. The case I was referring to before is, for example, it goes from 3.5 bar inlet pressure, 170 degrees C, to 13 bar roughly, because the 13 bar was picked because the steam system in that facility was on 13 bar level, 1.3. Is also doable to compress up to higher pressures. Yeah, like whatever would be the next how to say step in the network in the plant. Maybe 30 bar can also be done. So it's straightforward, and the technology is available. So we call it also MVR, mechanical vapor recompression, and it is it's a centrifugal compressor who is doing the job.
We have one question to you, Klaus. Where do you see all the hydrogen coming from? So will the hydrogen be mostly from the warm countries, I say? So will it mostly be sourced from Spain, Saudi Arabia, India, and Australia? How expensive will it be to come to the countries of high demand? And in relation to, it's not directly related, but I want to address this at the same time. There's somebody commenting on boilers using hydrogen. He says, seems we need to recirculate the exhaust gases to increase the CO2 and in order to make it more efficient. So what technology do you see fit for this? Klaus, can you get us started on this? So where's the hydrogen coming from? At what gas? At what cost? And also, do we need to recirculate the exhaust gases in the boilers to make it more cost efficient? They're not directly related, but I thought you might be able to answer both of them.
Yeah, I can certainly say something to the first question about where the hydrogen should come from in the future. There's a lot of project development going on in countries like Australia, Saudi Arabia, also something in North, West Africa, in South America. Those are countries that have huge potential for solar power and also wind energy, and produce low-cost hydrogen, green hydrogen. The next thing is how to transport this hydrogen to other continents over thousands of kilometers. And transport of hydrogen turns out that it's most cost competitive, or can be done at lowest cost when it is transported through a pipeline. Transporting by marine with big ships is also possible, either as direct hydrogen, liquefied hydrogen, or hydrogen stored in some like ammonia or methanol. This can be done as well, but it has then the disadvantage to have another conversion step in there, which costs money and efficiency. So the ideal situation is really transporting hydrogen via pipelines. That could be done probably from Saudi Arabia to Europe. Definitely can be done to transport it from Portugal or Spain to Central and Northern Europe.
Oh. I have a very nice question here. Straightforward. At what CO2 price would everybody rush to install a CCS project? Sorry.
100 euro.
And why? Please elaborate.
Yeah. Well, so far the CO2 price was rather low. In the past, it was, at least in Europe, it was maybe 5 euro per ton. Then it increased to maybe 25, and then last year during Corona, it fell again to 17. So there was never a real, how to say, push or incentive or a threat, for however you want to call it. So now it's climbing, and it's now probably at around 60. And okay, so, and still there's a lot of discussion and planning, but so far, yeah, there's not the movement what we would need. So okay, so maybe it's the 100 comes from various discussions I heard before. So maybe it's because of that. So yeah. But again, also the legislation and politics also they need to give their, let's say, the guidance and the.
The same gentleman is asking, is it feasible to have a car running on natural gas with carbon capture? And is this economics in terms of cost per mile? I mean, this is also hard to abate industry. It's not only steel and cement, and yeah, the transport is one of the biggest emitters of all. So Andrew, what is your view on this?
Yeah, the answer is it would be very difficult to make that feasible, and so the path to decarbonizing transportation, I think, will be through electrification and hydrogen, and then we can do the carbon capture, right, to create blue hydrogen, as Klaus indicated, so that you have low carbon hydrogen going into vehicles. We can do carbon capture at fossil fuel power plants to reduce the carbon footprint of the power going to the batteries in electric vehicles. That's, I think, the most likely path for decarbonizing transportation.
Then somebody coming from the shipping industry says a typical steam turbine vessel will use about 170 million tons of fuel oil per day. Hence, something like 350 million tons of CO2 per day. Can this be handled with CCS without requiring a new engine room? So does it actually fit into a normal vessel? I guess the answer is not at the moment.
Well, those numbers we'll have to kind of look at, but I will say that we also have a collaboration with TICO 2030 in Norway, where we are actually working on a design for maritime applications of our carbon capture technology. Footprint, we know, is very valuable, right, on a ship, both for the carbon capture technology, but also for the CO2 that needs to be stored once it's captured aboard the ship. And so those are things we're looking at right now in detail with TICO 2030.
Another idea would be also to apply a waste heat recovery from let's say, if the ship is driven by a gas engine, then the exhaust gases could be used. That heat could be used to drive a supercritical power cycle producing electricity. That could be an option as well and this electricity could be used then to maintain the ship certain electrical supply and so on. So the nice thing is supercritical CO2 machinery is very, very compact and small and fits nicely to a vessel where space is a concern. Yeah.
Anja, could I comment really quick on part of one of the previous questions? Just because I think for this audience, I kind of, this is selfish. I want to kind of put this idea out there, emphasize it. Somebody asked about recirculating flue gas in engines to increase the concentration of CO2, and I think that's something that isn't being looked at as seriously as maybe it should be, especially if you have a gas turbine application. What you essentially can do is recirculate the exhaust gas to displace some of the nitrogen going in the front end of the process, so that you have the same amount of inert gases going through your combustion system, but you're replacing some of the nitrogen with CO2, so that what's coming out the back end is a more concentrated CO2 source. And that's a way to decrease the cost of carbon capture on the back end of your process and optimize your system so that you can have better economics from a carbon capture perspective. And major engine and turbine suppliers have looked into that, and I think it's something that anybody who's doing gas to power should probably be aware of, at least as kind of an option for how you can optimize your process for carbon capture.
Yeah, we've written about that actually. There's a lot of questions on enhanced oil recovery. I'm not going to go into this because this is a complete different topic. This would be for a future webinar. Instead, I want to go back to the more down-to-earth applications. The greenhouses, one of which I visited myself. So how can we run greenhouses carbon negative, carbon neutral? How can we run them fully on hydrogen? And what other options do we have? Because they might be smaller than, let's say, cement, but they are not less important. So Klaus, floor is yours.
Yeah, thank you, Anja, for this question. That's certainly a very interesting and nice application, greenhouses. And you mentioned you bring this question to me because we have done a lot of applications for this, putting in engines that provide electricity for lighting, heat for heating the greenhouse, and CO2 for increasing the growth of the crops and vegetables. And using that CO2 from the engine could increase the growth of the vegetables and crops by about up to 30%. What we do, in the past, we're still using natural gas as the fuel, but we're concentrating the CO2 and bringing the CO2 in a concentrated way to the crops. What is the future? The future could be that we replace natural gas, or our customers replacing natural gas by biomethane. Biomethane is carbon neutral. And in the same way, we are bringing the CO2 concentration to the crops, and that helps to grow the crops much better than without.
Interesting.
But also, when hydrogen could be used, but the problem with hydrogen is there is no CO2 anymore. We can still produce electricity and heat, but there is no CO2 anymore.
Mm-hmm.
But then the CO2 could be replaced by direct air capture.
Mm-hmm.
Yeah, have a direct air capture unit installed and bringing it directly to the greenhouses and using this as a fertilizer.
In this case, the whole application would be carbon negative.
It could be, yes, it could be carbon negative.
Yeah, nice, very nice one. Then to Andrew and Ulrich, I understand you guys are actually working together somewhere in upstate New York. Please tell us more.
Yeah, well, sure. I mean, both Atlas Copco as well as Chart have, how to say, applications where we have joint activity in terms of that the equipment of Chart is used for the process side, and Atlas Copco is supplying the rotating machinery. For example, one project comes to my mind for hydrogen liquefaction in this case, where the cold box and so on comes from Chart, and the rotating machinery comes from Atlas Copco. So that is used for hydrogen liquefaction for a customer who's involved in the whole, let's say, whole supply chain of hydrogen to make use for fuel cells. So I think that is a nice example, and of course, that is also the way to go further. I mean, to have our ideas combined, let's say, and fulfilling the ideas of our customers. That's what we need, I believe. Yeah.
So you're already bringing us into the future. We understand there's a lot of technology around. Some projects are already at large scale profitable, others are in the making. There's also some regulation in the making and debated in the US Senate. I'm talking about the 45Q tax credits. which I understand are running out soon. So Andrew, talk us through this. What is this scheme all about? Is it still enough of an incentive for projects coming in the future years?
Yeah, so in the United States, the most significant nationwide CO2 incentive that we have right now is the 45Q tax credit. There are other regional incentives in voluntary markets. California is the most notable, state that's doing its own cap and trade system, and they have their own incentives for low carbon fuels and things like that. But nationwide 45Q is the big one. 45Q currently offers a tax credit for CO2 that is sequestered or used, and that tax credit is applied to projects that are large enough and that get implemented before 2026, as you said, Anja. But that is, as you said, part of what's being debated right now is some of these big spending bills that are going on in the United States Congress right now. So there are proposals to extend that beyond 2026. Current tax credits would be about between $35 and $50 per ton of CO2 captured and sequestered, depending on how you do that. There are proposals to increase those numbers to $60 and $85, which would definitely incentivize more projects. They're also importantly, I think, especially when we're talking about smaller CO2 sources, like we might be talking about with natural gas powered engines and those kinds of things, there are proposals to reduce the minimum size that's required to access those tax credits, so that a compressor engine in the field or something could qualify for 45Q tax credits, whereas right now it would be difficult for them to do that.
Very interesting. Are they planning to come to a decision, let's say, by the middle of next year? When do you see actual facts on the table for the industry to invest?
Well, it does appear some of this is getting close, but I will not. I won't present myself as anyone who can predict when the United States Congress is going to get a bill signed or passed. So we'll find out. I think that there's some possibility of having these changes in place this year as part of the current infrastructure bill, but we won't count those chickens before they hatch. So.
Yeah, sure. Good to have you on board. You're the US representative. That's why all these questions are thrown at you. So looking at Europe, we have a pan-European emission trading scheme, prices too low. Klaus and Ulrich, what else do we need? Do we have a need to introduce an additional carbon tax, maybe on a national level? Do we need to reduce the number of allowances? Do we have to force the energy intensive industry, let's say steel or transport, maybe even the car industry, to be part of the emission trading scheme? I hear them cry out already. So what do we need?
Yeah, that's a very interesting question, and a very political topic in many countries now in Europe. We just entered the phase 4 of the European emission trading system. I think it was this year. And when we look back the last 10, 15 years, there were a lot of modifications necessary in this EU ETS mechanism, because the result was not really what politicians wanted to see. The price was very low over a very long time. And as a result, for example, the UK put in a carbon floor price. Yeah. And the result of this carbon floor price was that the coal plants in the UK were not competitive anymore against gas-fired power plants. In Germany, it was the opposite. The coal plants were more competitive than gas plants, so they were producing over many years the majority of electricity.
So are you saying we need a pan-European carbon floor price?
So when we look now at the bigger picture at other countries, what they do, there are already carbon prices in place in countries like Sweden or Switzerland, where they have carbon prices above 100 euros per ton. in the range of 120, 130 euros per ton.
Right.
And more and more countries are putting in carbon prices for all the other fossil fuels that are not covered under the ETS. Germany put it in a carbon price starting with 25 euros per ton and now going to 30. I think this will be more accelerated to higher prices. Other countries starting, like in Austria, we're starting at 30, 35 euros per ton. I think most of the countries will go quickly to about 100 euros per ton. And
So the
I
question
agree.
is, can we centralize this? This is supposed to be a European Union. So can we have a level playing field on a carbon price and then agree on which industries we want to include?
Yeah.
Because otherwise, everybody will rush
Exactly.
and produce somewhere else.
This is also another topic. Should we have harmonized prices in Europe, or should every country put in their own prices? I think this is still under debate, and both could happen. Yeah, we could have European-wide carbon prices or country individual prices. Those could happen. But I agree with what Ulrich said before, that we need a carbon price above 100 or more to have a real change in industry and doing more carbon capture storage as well.
Can you come in, please? So do you see a pan-European carbon price, and do you actually see that various hard-to-abate industries will be included, even if they are lobbying hard against this? So is there some change coming?
Yeah, well, to harmonize it across Europe would be, of course, great. This is then the challenge for the politicians sitting in Brussels, and yeah, okay. So hard to comment on that, and if it's doable, yes or no. I'm probably not the right person to say that, but it would definitely, yeah, help. And yeah, on the other question. That was regarding, help me out here again. What was the other question?
Do we see a pan-European carbon price? I know this is difficult to answer. And do you see that the cement makers, the car makers, the steel industry, not only the power plants, that they all be included, shipping as well?
Sure, at the end, everybody still needs to earn money and needs to have a business case. Also, we see that all companies have now, let's say, the zero emission targets, or let's say, or reduction targets, and so on. So also the oil and gas industry, they have all these initiatives around renewables and so on. So I would say, yeah, if they let's say mean it's seriously, then they should also pay for the bills. Yeah. So I think that is needed. Otherwise, it will be hard for the generation afterwards, after us, to live in a clean environment, right? So that is.
So now for everybody, imagine we meet again in 5 years' time. Which big projects will we have implemented, which we have not implemented today? Andrew, what is the technology just about to happen and the project?
Yeah, so with so we have a project that we announced a couple of weeks ago on cement, and so I hope 5 years from now to be telling you that project was successful and we've moved on to larger and more projects like that. But overall, it's really the near-term projects are going to be the ones where you have all the right pieces. So you have an offtake, you have a price, you have a CO2 emission source, and you have a regulatory environment that are conducive to that. And those are going to be the early adopter projects, because we are in the early stages of this market coming together. And I think this panel represents a good group of different technology providers that can work together to innovate the things we need to then work down the cost curve and expand from there.
Right. So the cement industry is coming forward. What about steel making? Is it one of the more difficult ones? And also the car industry, what are the hard nuts, the difficult cases?
Steel from a CO2 concentration perspective is a pretty good industry, actually, similar to cement, has high CO2 content if it's being produced in certain ways. And so steel could be a good early adopter as well. The more difficult ones will be the remote, the portable, and the low CO2 concentration sources. So
yeah. Ulrich, what do you see in 5 years' time? So
Yeah.
where will there be the big projects and what industries are coming forward?
In terms of decarbonization, I would say in 5 years, we see that there is, of course, there's more renewable energy available from wind and solar, which needs to be stored because of the periodical changes. So we will see more energy storage that we will see in larger scale, that we will see in 5 years. And in 5 years, probably we will have also done more, how to say, developments on the hydrogen side. So we will see, not an uptake in hydrogen, but we will see more activity in hydrogen in after 5 years. I would think so. That we see more on the transportation side and liquefaction side, and on that side we see that in a broader scale, not fully commercially, but going there, yeah, in 5 years.
So energy storage and hydrogen.
Yeah, that would be okay. Both hydrogen is also an energy carrier, so it means basically storing of energy and transportation of energy. Because to make decarbonization happen, you need to have more renewables, and that means also then at the end storage. And there's different storage concepts available: thermal energy storage, or liquid air energy storage, or other storage means, or of course also hydrogen beside others. Yeah.
So Klaus, basically we are looking at integrated projects, storing energy, hydrogen co-firing. We addressed this in our very first webinar on integrated decentralized power projects. Where do you see the future in terms of carbon capture and reuse? What is your core application, or where do you see the industry going?
Well, I think at the moment there's a lot of talking about green hydrogen, putting in electrolyzers. And I think within the next 5 years, we will see a lot of electrolyzer deployment, different technologies of electrolyzers, producing some green hydrogen. But the key element that helps to scale up hydrogen and build up a hydrogen economy, I think, is producing low carbon hydrogen from natural gas using carbon capture storage. That will help us to be fast and scale up hydrogen economy fast and have a real impact on the energy transition for many industry applications, as mentioned, cement, steel making, chemical industry, oil and gas, etc.
Very interesting. So I have quite some ideas for future webinars, and I want to thank everybody for a very lively discussion. I want to thank everybody out there who has been listening and has been supplying us with interesting questions. Feel free to address the panelists individually after the webinar, or write to Get the Power Journal with ideas, articles, you name it. So thank you, everybody, and see you again soon. Bye.
thank you.
Thank you. Bye-bye.
Bye-bye.